somebody stop me in about an hour because I'm going to have to swap out the battery on this thing. All right, let's get started then on this stuff. There's where I want to start. Okay, what we did last time was we developed the theoretical background for analysis of variance. All right? And I think I have that video up on the web page, so if you understand that, you are home free, because the rest of the semester is just an extension of that. It's easy peasy. All right? There's one thing that I want to point out before we move on. Okay? And that is, I want to talk about error. And what I mean by error is making mistakes. Okay? And I'm going to look at two different types of errors. And we can make this little table, and over here on this axis, we're going to say, well, one option is that we're going to reject the null hypothesis. Remember, the null hypothesis is the hypothesis of no difference, and the alternate hypothesis is the hypothesis of some kind of difference. So here, one option is that we reject the null hypothesis. The other option is that we not reject H naught. Notice I don't say accept H naught. I talk about reject or not reject. Okay? Now, the two possible scenarios is that H naught could be true or H naught could be false. Okay, so now we have our little table like this. And let's look at what happens, all right? If H naught is true and we do not reject it, that's great, no error. If H naught is false and we reject it, that's great, no error. On the other hand, if H naught is true and we reject it, that's called a type 1 error. And the type 1 error occurs with the probability of alpha. So if you set your alpha value at 0.05, that means you have a 5% chance of committing a type 1 error. All right? It also means you have a 95% chance of not committing a type 1 error. Right? So if you set alpha at 0.05, that means you're going to be right 95% of the time, but 5% of the time you're going to commit a type 1 error. If H naught is false, but you don't reject it, that's called a type 2 error. Okay? And a type 2 error occurs with the probability beta. Okay? So we can control the type 1 error rate by controlling alpha. Okay? The problem is, how do we control beta? Okay? All right, well, let's make a few observations about beta. All right? So, beta is equal to the probability of accepting H naught given that H naught is false. So that's how we make probability statements. To capital P says the probability of, now we have the event in parentheses. This vertical line right here indicates that it's conditional. So the probability of accepting H naught, given that H naught is false. So that's equal to beta. So 1 minus beta is the probability of rejecting H naught when H naught is false. Okay? So 1 minus beta equals the probability of rejecting H naught, given that H naught is false. And that is equal to the power of the test. Okay? So what we're trying to do in this class is come up with experimental designs that maximize the power. So we're trying to increase the probability of rejecting the null hypothesis, given that the null hypothesis is false. We can control this with alpha, but alpha and beta are not perfectly related. All right? So now the question is, what can we do to control beta? We can make a few basic observations. All right? The first observation that we can make is that as we increase the variance, then we get an increase in beta. Right? That's the type 2 error. Okay? So as beta gets larger, that means the power gets smaller. So as your variance gets larger, your statistical power gets smaller. Everybody see that? As you increase the sample size, then you get a decrease in beta. So as your sample size gets larger, the type 2 error rate gets smaller, and therefore your power gets larger. So you want more statistical power? Get a bigger sample size. Notice, as n gets larger, the variance gets smaller. Okay? Why is that? Because the variance, the sample variance, right, is the sum of yi minus y bar quantity squared divided by n minus 1. So as n gets larger, right, this whole thing gets smaller. And finally, as delta, which equals mu1 minus mu2, right, as you decrease delta, then you increase beta. So as the difference between your treatment means gets bigger or gets smaller, your type 2 error rate gets bigger, and therefore your power gets smaller. Okay? So if your differences between your groups get really, really, really small, your ability to find it is going to be reduced. All right? So now when you're reading scientific papers, think about type 1 and type 2 error rates. Type 1 can be controlled with alpha. Type 2, the only really option you have with type 2 is to think about sample size. Okay? Because the data are variable, right? As you increase sample size, you're going to make the variance smaller, which is a good thing, right? You don't really have a lot of control over that thing right there, so the thing that you can control is your sample size. So you want the biggest sample size possible.
And you said that as the difference between the means gets smaller, beta gets larger?
Yes, the probability of a type 2 error increases.
Okay.
Okay? All right. So we know about t-tests. We have two groups. So let's now start talking about ANOVA. We've done the theory behind ANOVA already, sort of the graphical representation. We know why we're doing it. It's that Bayesian problem, okay? So if you have more than two groups, then suddenly we run into this sort of conundrum with doing all of these pairwise comparisons, and we'd like to avoid that. Let's do an example, okay? Let's imagine we have 4 treatment groups, and your homework for this week is going to be use R to do this problem, okay? So I'm giving you an ANOVA problem, and I want you to use R in order to come up with precisely the result that I've gotten with data using hand calculations, all right? So we have 4 treatments. Our first treatment is no fertilizer. Okay. Our second treatment is K2O plus nitrogen. Our third treatment is K2O, which is what? K is potassium. No, yeah, potassium, right? So potassium plus a phosphate, P2O5. And then our fourth treatment is going to be nitrogen plus a phosphate. Okay? So we have treatment 1, treatment 2, treatment 3, and treatment 4. And we don't need to compare treatment 1 with treatment 2. But what you see is we need to compare treatment 1 with 2, 1 with 3, 1 with 4, 2 with 3, 2 with 4, and 3 with 4. So we've got 1, 2, 3, 4, 5, 6 possible pairwise comparisons. So if we want to do t-tests in order to do all of these comparisons, then what we're going to use is we're going to use 1 minus alpha divided by 2s, where s is the number of pairwise comparisons. So if we want an alpha equal to 0.05, okay, what we're going to have to do instead to maintain that type 1 error rate is use a tabled alpha of 0.0042. Okay? So if we're doing 1, 2, 3, 4, 5, 6 pairwise comparisons on these data, when we look up the value, the t-statistic in the table, we're going to have to look for the t-statistic that corresponds with 0.0042 instead of 0.05. And if we do that, then we'll be guaranteed that our true p-value is 0.05. Okay? So we're protecting ourselves against that Bayesian problem. Remember the problem with the ping pong balls. Every time you take a ping pong ball out of the hat, right, you've learned something. Every time you do one of these comparisons, you know, hey, 1 and 2 are different. Hey, 1 and 3 are different. There's something up with 1. Okay? 1 and 4 are different. You now know something. Okay? So the true probabilities have changed. Okay. So let's use the following data. All right? I'm going to, for my control group, my data are going to be these. I'm just going to, you have this stuff written down. Okay, good. My control group, let's see, I'm just going to put C, K2O plus N, K2O plus P2O5, and nitrogen plus P2O5, okay? I'm going to have a balanced design. So my I goes this way. I1, I2, I3, I4. My J's are going this way. And I'm going to have 6 observations for each treatment. Okay? So I've got 99 bushels, 40 bushels, 61, 72, 76, and 84. Here I've got 96, 84, 82, 104, 99, and 105. 63, 57, 81, 59, 64, 72. And here I've got 79, 92, 91, 87, 78, and 71. Okay? Now, I'm going to add a little column over here, and this is going to be the sum of y, I, j, okay, from I equals 1 to 6. And then this is going to be yi dot bar. All right, so here I've got 432. Here I've got 570. Here I've got 396. And here I've got 498. And then, how am I going to get yi dot bar? That's going to be 432 divided by 6, right? That's 72, 95, 66, and 83. Okay? Now, we need to make a couple of assumptions. How do you spell assume?
Makes an ass out of you and me.
Yep. Assume. Assume. Okay? We have to make a few of those. The first one that the first assumption that we're going to make is that our 4 samples are independent random samples from the overall population. Okay? Or from 4 separate populations. We have a population of controls, a population of this, a population of that, a population of that. And we're sampling. We're taking 6 samples from possible controls, 6 samples here, and so on. So our samples are independent random samples. We're also going to assume that each of these 4 populations are normally distributed. Yeah.
So on the right there, the 2 columns after the observations, that's the sum and then the mean.
Yep, that's the sum. So 432 is 99 plus 40 plus 61 plus 72 plus 76 plus 84. Okay? So we're going to assume that those numbers are normally distributed. Here's the problem. There are lots and lots and lots of statistical tests out there for normality. All right? Lots of them. The problem is that none of them are very good. So anytime somebody says, yeah, we tested for normality using this test, you're going, fine, whatever. Okay? you're better off just looking at the box plots. So whenever you do an ANOVA, including on your homework here, the first step is to make a box plot, side-by-side box plots, okay? And that's just as good as any statistical test for normality. The good news is that analysis of variance is remarkably robust with respect to moderate deviations from normality. So even if your data are not normally distributed, that's usually not such a bad thing with ANOVA. You can usually get away with it. There is another option. If you know that your data are not normal, there is another way of doing ANOVA. It's called a non-parametric ANOVA, which is going to be distribution-free. We'll do an example of that later, not today, but at another time. All right. The other observation, or the other assumption that we're going to make, is that the variances of the four populations are equal. That's referred to as homoskedasticity. Homo, meaning the same. Skedas, S-C-E-D-A-S-T-I-C-I-T-Y. Homoskedasticity. My kid brother was a big shot in Skida. So I used to give him a ration all the time about, is that homoskedasticity? Or what is that, man? It stands for Southern California Econorail Dragster Association. Something nobody does anymore. But back in the day, that was a big deal. All right. He liked to go fast, really fast. He once crashed going 240 miles an hour. Pretty exciting. Fun to watch. It was exciting. He walked away from it, so it's not cool. All right. As opposed to heteroskedasticity, meaning the variances are different. So here, the variances are the same. Here, the variances are different. Okay? Well, you can determine that with your box plots. And that's actually more of a bugaboo than is the whole notion of normally distributed data. What if you look at your box plots and you go, oh man, there's no way the variances are equal. There is no way my variances are even close to being normal. What do?
Transform the data.
You do a data transformation. And I will give you a sheet on how to transform your data, what sort of approach to take, depending on what the data looks like. Okay? All right. The final observation that we're going to make is that the observations are independent of one another. That is, that observation is not dependent on that one. Okay? So in other words, if I ask you your age, that in no way affects anybody else's age. Okay? All right. Everybody has those numbers written down? Because when you do this assignment, you will need to type those numbers in. So you'll create your own CSV file, okay, and input those data. I will give you a sample of how to do one-way ANOVA in R. I'll do a little video, how to do the script and all that, how to set up that whole thing again. Just a short 5-10 minute little video. I'll use a different data set. Okay? All right, let's think about, we had this column of means over here. Let's think about what those are. for the population, not for the sample, mu1 is equal to mu plus alpha 1. Mu sub 2 is equal to mu plus alpha 2. Mu sub 3 is equal to mu plus alpha 4. Whoops, alpha 3. And mu sub 4 is equal to mu plus alpha 4. Remember, that's that whole idea from last time. Right? Where here's mu, and there is, if this is I equals 1, this is going to be alpha 1. Okay? And what's that term right there? That was epsilon. Epsilon 1. Okay? Actually, it's going to be epsilon 1j. All right?
What's the difference between an observation and a mean?
Yes, of that treatment mean. So if that bar right there is the treatment mean, the alpha is the difference between the overall mean and the treatment mean. And then the error term is the difference between any one point and the treatment mean. So alpha I then is equal to mu I minus mu. So that alpha is the effect of that treatment, and importantly, the sum of all the alpha i's is equal to what? All right. I asked Billy Bob, how old are you, Billy Bob? And he says, I'm 20. I asked Joe Bob, how old are you, Joe Bob? He says, I'm 22. I asked Bobby Ray, how old are you, Bobby Ray? He says, I'm 18. So what's the average age? 20. Okay? What's the alpha between 20 and 22? 2. What's the alpha between 20 and 18? Minus 2. What's minus 2 plus 2?
0.
Okay?
Okay.
All right. We're only going through this level of detail one time. After we establish this, for every other design that we look at, we won't have to do this. We just have to go through this first time. So our individual observations are y, I, j, and we say that those individual observations are I, N, D. That means independently normally distributed. IND, independently normally distributed, with mean u plus alpha I and variance sigma e squared. Right? Such that the sum of all the alpha i's is equal to 0 for I equals 1 to A and j equals 1 to n. Where A equals number of treatments, and n equals number of observations in each treatment. Okay? All right. The kind of ANOVA that we're doing today is called a CRD. So we're going to learn a bunch of ANOVA designs. The one we're doing today is a CRD ANOVA. CRD stands for completely randomized design. Okay? And it's referred to as a Model 1 ANOVA. And what I mean by a Model 1 ANOVA is that it has fixed effects. Okay? My treatments are fixed. It's either control, or nitrogen plus phosphate, or potassium plus nitrogen, or whatever. Okay? Those treatments are fixed. My model is, and we already did this last time, Yij is equal to mu plus alpha I plus epsilon ij. I know that the sum of the alpha i's is equal to 0, and I also know that the epsilon ij's are identically normally distributed with mean 0 and variance sigma e squared. All right. Everybody's with me up to this point. It's just definitions. Okay? You're never going to have to take a test on it. Now what we want to do is we want to estimate our parameters. Okay? We want unbiased minimum variance estimates of u, alpha I, and epsilon. Okay? All right. Let's start with yi dot bar. That's equal to yi1 plus all the way to yin divided by n. So I'm going to take, for the ith treatment, I'm going to add up all the observations in the ith treatment and divide by n, which is the number of observations in the ith treatment. And that then gives me the treatment mean for the ith treatment. The expected value of yi dot bar is equal to u plus alpha I plus all the way to u plus alpha I, all of that divided by n. Oh, wait, you say. Well, sure, because what's the expected value of yi1? What's the expected value of the first observation in treatment I?
99.
Pardon?
99, using the data from before.
Yeah, but that's the sample.
Oh.
We're talking about the population. Well, it's going to be the true mean plus the treatment effect. And it's going to be the same for each of those. That's why it's mu plus alpha I plus mu plus alpha I plus mu plus alpha I plus mu. It's always the same. Okay? And then I just divide by n, which equals n times mu plus alpha I divided by n, which is equal to mu plus alpha I. Yeah. So the expected value, what's the expected value of the ages of Billy Bob, Joe Bob, and Bob Ray?
20.
20. Okay? That's all I'm saying right here. Okay? Same thing. All right. How's about y dot dot bar? That's equal to y11 plus all the way to y1n plus ya1 all the way to yan divided by a times n. There are a times n total observations, right? There are n observations in each treatment, and there are a treatments. So a times n is the total number of observations. So then the expected value of y dot dot bar is going to be equal to mu plus alpha 1 plus mu plus alpha 1 plus mu plus alpha A plus mu, oops, plus dot 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 mu plus alpha A. All of that divided by an, which equals an mu plus n times alpha 1 plus dot 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 alpha A divided by an, which is equal to mu plus alpha 1 alpha A divided by n, which is then equal to mu. Because some of those are going to be positive and some of them are going to be negative. All of the alphas taken together are equal to 0. Okay? So all of that part adds up to 0, which means I end up with mu. And then finally, it's just playing around with the rules of expectation and variance is all. And then finally, how's about alpha I? Our estimate of alpha I is going to be equal to y dot bar minus y bar dot dot. We've already established that. Our estimate of sigma e squared, the little hat means it's an estimate, is equal to se squared. Our parameters and our estimates. For mu, that's our parameter. Our best estimate of mu is y bar dot dot. Our best estimate of alpha I is going to be yi dot bar minus y bar dot dot. Our best estimate of mu plus alpha I is going to be y I dot bar. Our best estimate of sigma e squared is going to be s e squared. And our best estimate of epsilon is going to be yij minus yi dot bar. Okay. Let's use those estimates. All right? Remember what our model is? Our model is y equals mu plus alpha I plus epsilon ij. There's that. There's that. There's that. Okay? I hate erasing this stuff, but so when I was an undergrad, there were a couple of courses that I hated. And there's a reason why it was not a pre-med. I hated with a blind, cold passion microbiology, and I hated genetics. And genetics, I had two genetics professors. They co-taught this course. And the first guy was this Navy guy. Big, big, gigantic arms, man. He was just this real muscular sort of ex-Navy guy. And he'd teach, this is back in the day, cup of coffee in one hand, holding it like this, and sticking out right here was a lit cigarette. He smoked the whole class. He'd take a sip, take a hit off his cigarette, and then work on the board. And the classroom had blackboards around three sides. He'd start the lecture over in that corner, and he'd just start this example, and he'd just go all the way around the room. And the class is 50 minutes long. 45 minutes into the class, he's finished up over there on that side. This long exposition of some genetic problem. He gets to the end, he sits there looking at it, takes a sip of coffee, hit off his cigarette, exhales, another sip of coffee. He goes, nah, that's not right. Starts erasing the whole thing all over. Kids are pulling out their notepaper, tearing up their notepaper, throwing it away. 50 minutes, you got nothing.
Why didn't you pursue like engineering or something?
Nah, my father was an engineer, and I hated my father.
No.
It was the last damn thing I was going to do. Anything to please him was off the playlist. All right. So we're in like Flint, right? Because let's replace these things with the estimates, okay? So we've got y, and you're asking yourself, why the hell are we doing all this stuff? You'll see in just a moment. So yij is equal to, and then our best estimate of mu is y bar dot dot, right? And then plus alpha, and our best estimate of alpha was yi dot bar minus y bar dot dot. And then our best estimate of epsilon was yij minus yi dot bar. So let's take this and subtract it from both sides. So now I have yij minus y bar dot dot is equal to yi dot bar minus y bar dot dot plus yij minus yi dot bar. Okay? Then, let's square both sides. And add everything up across all i's and j's. So now we're going to have the sum across I and across j of yi j minus y bar dot dot, quantity squared, and that's equal to the double sum of yi dot bar minus y bar dot dot, quantity squared, plus the double sum of yij minus yi dot bar quantity squared, plus the cross product. But remember our assumptions. Our assumptions were that we had independence, and under those conditions, all those cross products go to 0, and we don't have to worry about it. Hey, look what we have. We have that equation right there, just that term right there. What does that look like? It has a special name. It's a sum of what?
Squares.
The sum of squares. More completely, it's a sum of square deviations. It's the deviation of observations from the overall mean. So it's a sum of square deviations. We call it, shorthand, just a sum of squares. That's a sum of squares. A sum of square deviations. Deviations of the treatment means from the overall means. This is a sum of square deviations of observations from the treatment means. So what we're saying is the deviation of the points from the overall mean is equal to the deviation of the treatment means from the overall mean plus the deviation of the observations from the treatment mean. Right? Awesome. We're home. We are home free. Let's put this up in a little table. Okay? When you write a paper, too often when people do this sort of a test, they write their paper, they just give you the F test. We did it in ANOVA. F was equal to this, P was equal to this, therefore this. And whenever I read that, I never believe it. I want to see the ANOVA table. Let the editor-in-chief remove the ANOVA table if he wants to, but I want everybody to see the ANOVA table. And that's especially important when we get into some more complicated designs. I just been reviewing a paper, and these people, the guy claimed, yes, we did this nested ANOVA. And I'm going, really, how could I possibly know? Because you're not giving me any degrees of freedom. You're not showing me what was what. I don't know what you used for your error term. Unless I see the ANOVA table, I have no way of knowing. And the guy responds, he says, what do you mean? And I said, well, he did all this in R, right? And he says it's nested. And I say, I don't know that how do you know that it's nested? Right? I need to see the sums of squares. I need to see the degrees of freedom so I know what you divided by what to get your F test. Then of course, push comes to shove, he wasn't doing a nested ANOVA at all. And the problem is that it totally changed the result. He was right to use the nested ANOVA, but he didn't perform a nested ANOVA. He performed something else, and he got a significant result. And after he really performed a nested ANOVA, the significant result was gone, which totally changed the paper. All right, so the first part of any ANOVA table is source. Followed by DF, degrees of freedom. Followed by MS, which stands for mean square. Followed by, whoops, I missed one. My bad. SS, which is not a German thing. It's not a reference to the new white supremacist movement. It stands for sum of squares. DF, which stands for degrees of freedom. MS. EMS, emergency medical services, which is what you'll need. No, not. It stands for expected mean squares. And then F, computed F, and then F table. Okay? So here are, when I say source, I mean source of variation. So here the first one is due to treatment. Well, our treatments were control, nitrogen plus potassium, nitrogen plus phosphate, and then phosphate plus nitrogen or something like that. The next one is residuals. Sometimes, and more appropriately, referred to as error. And then is total. Okay? So, the sum of squares due to treatment is going to be the sum from I equals 1 to A, there were A treatments, of yi dot bar minus y bar dot dot, quantity squared. But I had one of those for each treatment, or I have that, right, for each treatment. So I've got to multiply that times n. There were n observations in each treatment. Okay, so I'm summing across my observations. Okay? So it's for the ith treatment, treatment, the A's, right? A is equal to 1, A is equal to 2, A is equal to 3, A is equal to 4. Right? For error, I'm going to have the sum of yi j minus yi dot bar, quantity squared. But it's actually a double sum because I'm going to do that across all i's and across all j's. And then for my total, I'm going to have the double sum across i's and j's. So j is equal from 1 to n, I is equal from 1 to a, of yi j minus y dot dot bar quantity squared. All right, let's talk about degrees of freedom. Remember, we lose 1 degree of freedom for every parameter we attempt to estimate. How many parameters are we estimating? Okay? How many parameters are we estimating? How many parameters are we estimating? How many parameters are we estimating right here? 2. 2? Y bar dot dot is an estimate of mu. So we're estimating mu. So we're going to lose 1 degree of freedom there. Okay? So how many total observations do I have? An. I have A treatment groups and n observations in each treatment group, so A times n we had 6 observations and 4 treatments, so 4 times 6 is 20, right? Is that what we had? So we have A times n minus 1 degrees of freedom. Okay. Now, let's go to the next one. Well, let's go to the top one. What are we estimating here? What is y I dot bar minus y bar dot dot an estimate of? What parameter are we estimating there? Well, let's remember what the model is. The model is y I j is equal to mu plus alpha I plus epsilon ij. So here, we're estimating mu. What are we estimating there? Go back to that little table we had up on the board. Our parameters and our estimates. One of the parameters was alpha. That's what we're estimating right there. That's what y I dot bar minus y bar dot dot. That's our estimate of alpha. Okay? How many alphas are there? How many treatments are there? There are A treatments. So we lose 1 degree of freedom for estimating that, so we have A minus 1. Now, what are we estimating here? The error term. Okay? We're estimating the error term within each treatment for each treatment. Okay? So we have A times n minus 1. Okay? Look. This is magic. A minus 1 plus A times n minus 1 equals A n minus 1. A minus 1 plus A n minus A equals A n minus 1. A minus A, okay? So A n minus 1 equals A n minus 1. This plus this equals that.
Okay.
Well, that's what we said in the model. That, right? This minus that, right, is equal to that plus that. If you guys were all on acid, you'd be sitting back there going, oh, far out, man. In other words, the ANOVA model is additive. As long as we satisfy those assumptions that we had at the beginning, the model is additive. So, what's the mean square? Hey! The mean square is going to be this divided by that. So it's going to be the sum of squares for treatment divided by A minus 1. That's the mean square treatment. What's the MSE, the mean square error? That's going to be this divided by that. So that's going to be sum of squares for error divided by A times n minus 1. I could do that, but I don't have to. Why bother? I don't care about that one. Why don't I care about that one? Right? What are those things? What are these mean squares? What are they really? What do we have? We have the sum.
They're the parts of the total.
Yeah. We have a sum. Let's look at this one right here. It's a sum of yij minus yi dot bar quantity squared divided by a times n minus 1. Billy Bob is 20.
Yeah.
Bob Ray is 22. Joe Bob is 18. Okay? So we know what the mean is. What's the variance? The variance is the sum of xi minus x bar quantity squared divided by n minus 1. Let me write that thing over here. Sum of xi minus x bar quantity squared divided by n minus 1. Those two things look even vaguely similar?
Yes.
Yeah, they look exactly alike. So that's a variance. What the hell's that? A variance? So that's a bit, I'll be dipped in shit. That's why they call it analysis of variance. Okay? So that's a variance term. If I did this one down here, that would be the total variance. So this is the variance associated with error. This is the variance associated with treatment. I'll be dipped. Do you remember this whole thing right here? Right, where we had those treatment means and we're looking at the variation around those points right there. We are comparing that variance together with, you know, the total variance or the variance there. Right? Well, that variance right there is that one, and that variance right there is that one.
Okay.
So if I compare those two, then that gives me my one number that I'm looking for. The one number, the one digit, the one number that tells me is my difference, are my groups different or not? All right, to convince you of that, the first 5 years I taught this class, I would say, okay, let's now take this whole thing right here and compute the expected value of that. And then let's do the expected value of that. And the eyes of all the students would sort of glaze over and roll into the back of their heads. You know, they'd fall asleep or pull out that bottle of cheap bourbon out of their backpack and just sort of take a couple of hits and wishing they were anywhere but in this class. So we're not going to do that. So here's the point where I say, trust me. If you don't trust me, go home and prove it to yourself. And you can do it. You know enough with those rules of expectation to be able to figure it out. When I was working on my PhD, I had 120 acres in the mountains above Albuquerque, and I had this little 300 square foot cabin. It had no indoor plumbing. I had a propane light, and I had a wood burning stove. And I didn't have computers, personal computers back in those days, but I had my little manual typewriter, and I had my little kerosene lantern and all that kind of stuff. And that's where I worked on my dissertation. And I got this idea. I said, gosh darn it, you know, people always compute density estimates in this certain way. And there's this certain equation that we use for density estimates. And I'm going, I wonder what the expected value of the density would be if one animal died. So you're handling the animal and the animal dies, so you've removed it from the population. How does that change the expected value of the density estimate? So I spent like 72 hours going through all the rules of expectation, solving this problem, and it comes up with this beautiful little solution. So I write all this stuff up, man, I write up this little 3-page manuscript, and I send it off to get published, right? And the reviewers go, yeah, well, duh. Well, of course, because the answer is, you lose one animal out of the population size is reduced by 1. But I proved it. It was really awesome. I still have that manuscript, and one of these days I'm going to resubmit it and say, God damn it, this is really cool, publish it. I'm prouder of that paper than any other paper I've done since, because it's truly a beautiful little piece of work. All right, so trust me, I'm a scientist. The expected mean square, right, the expected value of the mean square is going to be sigma sub e squared plus 6, right, 6, put n, right, times sigma sub a squared. The expected value here is going to be sigma e squared. So now the question is, what's the appropriate f-test? It's trivial in this case. But if this were a nested design, or a Latin square design, or an randomized incomplete block design, it would not be so trivial. So the reason I want you to know what the expected mean square column is so that you can actually look at it and say, oh yeah, now I know what the expected value, or what the appropriate f-test should be. Well, you only have one option, and that's this divided by that. What happens when you do that? Well, you get sigma sub e squared plus n sigma sub a squared divided by sigma sub e squared, which is equal to 1 plus n sigma sub a squared divided by sigma sub e squared. So what, theoretically, is the smallest value of your f-test? Make sure we're still recording there. Yeah. What's the smallest possible value of your f-test?
1.
1. Because if you have 0 treatment variance, 0 divided by this is going to be 0, so the smallest theoretical value is 1. So when you do an ANOVA and you come up with an f statistic, a computed f, that's smaller than 1,
You've done something wrong.
well, or something's funky with your data, okay? That's the point at which you go, uh-oh, man, wish I wouldn't have looked at that, okay? Something's not right. All right? In reality, though, okay, if you have no significant effects in your data, what are you doing? If there is no variance there, then basically what you're doing is you're estimating sigma sub e in 2 ways. Because if sigma sub a is 0, then up here you're estimating sigma sub e, and down here you're estimating sigma sub e. So there are 2 separate estimates. They're not necessarily the same. So it is, in practice, possible to get this smaller than that. Okay? It does happen.
Okay.
But now you know what the appropriate f-test is. So you can then, there's your computed f right there, so it's going to be mean square treatment divided by mean squared error, and then you look it up in what the table is. Let's fill this in with the numbers from the data that we had up on the board earlier, okay? So I've done all those calculations. I did them a long time ago. I did them by hand. You know, nowadays when people write computer code, it's different than 40 years ago when people wrote computer code. Any of you ever have an Apple IIe computer? Probably not. It's all ancient. There used to be this little magazine for Apple II enthusiasts called, what was it called? Nibble or something like that. They had a contest every month. So you had to write a computer program to run on the Apple IIe that was just one line of code. And you were limited, just like Twitter, you were limited to a certain number of characters on this line. So you learned to be extremely efficient in how you wrote the code. Because memory was limited on those computers. You know, you had 64K, you know, or something. You didn't have a lot of memory. Nowadays, you buy thumb drives that have a terabyte of storage on it, you know. It's no longer necessary to be efficient the way it was back then. But that's what we want to do, is be exceedingly efficient. And what turns out, for all this stuff right here, there are calculator formulas. So from back in the day when you would use your calculator to do all these computations, there are calculator formulas. And I'll show them to you sometime. They're really clever, and they enable you to do all these computations with many fewer keystrokes than if you try and do it by hand. Okay? I actually took a course once in calculator formulas for statistical parameters. All right, let's fill this table in. All right, degrees of freedom for our data, we had four treatments, so we've got 3 degrees of freedom there. We have 20 there, and we have 23, so we have a total of 24 observations. 4 times 6 is 24. The sum of squares due to treatment is equal to 2940. The sum of squares due to error is 3272. And the sum of squares total is 6212. So 2940 divided by 3 is equal to 980. And 3272 divided by 20 is 163.6. And then 980 divided by 163.6 is 5.99. The table value for F is 3.10. So here's our F, right? Our table value is 3.10, and we are at 5.99. We're out here. So what do we conclude? This is the 95% region. What do we conclude?
We are greater than 5% confident, or 95% confident.
Yeah, if we reject the null hypothesis, we're 95% sure that we're making the right decision. Okay? So because our computed value is more extreme than the table value, we reject the null hypothesis. Okay? So when you do that problem in R, you should come up with exactly these values. R is not going to give you the expected mean square. R will give you this stuff, this stuff, this stuff, and it'll give you the computed F value. It will not tell you what the table's value is, but it will tell you what the p-value associated with this is, which brings up an important point. A lot of times people, oh, my p-value is 0.0000123, and they'll publish that. And that comes across my desk, and I say, no, sorry, dude, 0.01, it's less than 0.01. So they're really impressed that their p-value is that small. And they want to point that out in their publication. Their data are so good, look how small their p, that's bullshit, okay? The fact that the p-value is that small, that just means it couldn't really figure out what the exact value was anymore. All you really know is that your p-value was less than 0.01, or more importantly, less than 0.05, which is what you established initially that you are going to accept. So if you're accepting a p-value of 0.05, if it's 0.049, that's good enough. And that's just as good as 0.0000001. Okay? The fact that it's 0.0000001 doesn't mean it's really significant, and the 0.049 is just kind of significant. No, they're both significant. So don't try and jack anybody around. Don't oversell what you've got. The p-value is less than 0.01 or it's less than 0.05, that's all you need. Okay? All right, questions about that stuff? All right, so your homework is I will provide a little video, right, to do this with a different data set, okay? And all you need to do is use the code that I provide in that video. I'll put some sort of file up there that has the code on it, and then apply it to this data set, right? What we do next, we've done a one-way CRD. We're going to stick with one-way ANOVAs for a while. The next one we're going to do is called an RCD, which is called a randomized complete block design. Then we're going to do a Latin square. And then we're going to do a nested. And after we've done that, we'll do a two-way, or a cross-class, what's called a cross-classification design, which is the n-way ANOVAs, and from there we'll start talking about other sorts of linear models. All of these ANOVAs, if you look in R, they're under LM. The procedure is LM, which stands for linear model. And you're going, but it's not a regression. No, it's not. But it's Y equals mu plus alpha I plus epsilon ij, which is linear. So it is, in a very real way, a line. Okay? And the difference between ANOVA and regression models is just one assumption. Okay? We're basically doing the same thing. So when we start regression models, all the hard work has already been done. All we're going to do is say, oh, hey, we have this extra little thing that we're going to use, and we're good to go. So it'll go very quickly. This will go very quick. That'll go very quick. This one, we're going to scratch our heads a little bit and think, okay, but it won't be hard. We've done all the hard work now. Everything hard in this class is behind you. So now we're just going through a series of designs. Okay? Mm-hmm. Awesome. See you guys next week.
And then about the gear stuff, you want us to run that next week?
Yeah, so, yeah, you can either email it to me, right? Make sure in the subject line you say ED homework, okay, or XDes homework or something like that.